Come to the next question, third question. Determine whether the relation R in the set A is equal to 1, 2, 3, 4, 5, 6. Defined as, the relation R is defined as set of all ordered pairs x, y such that y is divisible by x. This is the given relation R. Okay, my dear children. Now we have to check whether this relation R is reflexive, symmetric or transitive. Okay, now come to the solution. First we write the given set. What is the given set? A 1 2 3 4 5 and 6. What is the given relation? Set of all order pairs x comma y such that y is divisible by x. What is meant by y is divisible by x? It means x divides y, isn't it? X divides y. Now we write the ordered pairs. We write this relation in the roster form. What are the ordered pairs satisfied by this relation? Okay, my dear children. Therefore, R is equal to set of all ordered pairs 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 4, 2, 6, and 3, 6. These are the elements. These elements only satisfy this rule. These elements only satisfy this relation between x and y. Only these elements satisfy the given condition between x and y. Okay, therefore we wrote the relation R in the roster form like this. Understood, my dear children? Now let us check whether the given relation is reflexive, symmetric and transitive or not. Okay, my dear children. What is the first relation? That is a reflexive relation. Okay, if we observe the ordered pairs in the relation R, what do you find? The number of doublets or as many elements are there in the set A. Therefore, it means what do you get? What do you get here? Ordered pairs a comma a belongs to R for every a belongs to a. This is nothing but the definition of a reflexive relation. The given relation satisfies this property. Therefore, we can say that R is a reflexive relation. Now, go to the next relation, that is a symmetric relation. If you observe the given relation R, what you get here? There is a ordered pair 1, 2 belongs to R. But its reverse order. It means ordered pair 2, 1 does not belong to R. Okay, observe that given relation. It means, okay, my dear children, if ordered pair A, B belongs to R, implies that ordered pair B, A belongs to R for all A, belongs to A is not satisfied here by the given relation R. This is the rule. This is the condition for a symmetric relation. Okay, my dear children. This condition is not satisfied by the given relation. Therefore, we can say that R is not symmetric. Okay, my dear children. Understood? Now go to the next relation, that is a transitive relation. To prove this transitive relation, we take a link ordered pairs like this. We assume that the link ordered pairs are there, already there in the relation R. So we assumed that here ordered pair x comma y ordered pair y comma z belongs to R. Okay. Ordered pair x comma y belongs to R means, what is meant by ordered pair x comma y belongs to R? It means x divides y. By the given relation, we can write this statement. Similarly, ordered pair y comma z belongs to R. What is meant by ordered pair y comma z belongs to R? It means y divides R. We can consider this is a second statement. If you observe these two statements 1 and 2, from 1 and 2 we can say that x divides z because x divides y divides z. That implies that we can say that x divides z. Implies that x divides y z. X divides z means we can write like this: ordered pair x comma z belongs to R because the elements x and z are satisfying this rule. Understood, my dear children? Now come to the question number 4. Here, my dear children, I did not write the question, just I am writing here solution. Okay, my dear children, see the textbook. What is the question there? Okay, now come to the solution. Now we check whether the given relation is reflexive, symmetric and transitive or not. Okay, so first let us consider x belongs to z, means x is an integer. Okay, then we know that x minus x is equal to 0 is an integer. X minus x is equal to 0 is also an integer. This implies that order pair x comma x belongs to R. Okay, my dear children. Therefore, order pair x comma x belongs to R for every x belongs to Z. This is nothing but the definition of a reflexive relation. So the given relation is satisfying the definition of a reflexive relation. Therefore, we can say that R is reflexive. Now come to the next relation, that is a symmetric relation. For that, we assume that order pair x comma y belongs to R. Directly we assume that order pair x comma y belongs to R. Means the elements x and y are satisfying the given relation. Okay. Now x comma y, order pair x comma y belongs to R means x minus y is an integer. Okay, this is a given relation satisfied by the elements x and y. This implies minus of x minus y, minus of an integer is also an integer. We know this rule. So minus of x minus y is nothing but y minus x. Y minus x is also an integer. Okay, my dear children. Yes, right. This implies sorted pair y comma x belongs to R. Okay, at the beginning we assumed that ordered pair x comma y belongs to R. Finally we got this statement, that is ordered pair y comma x belongs to R. Therefore we can say that R is symmetric because it is satisfying the definition of a symmetric relation. Now come to the next relation, that is a transitive relation. To prove that or to check whether the given relation is transitive or not, directly we take the link ordered pairs. These two are said to be link ordered pairs belongs to R. These two ordered pairs are said to be link ordered pairs or connected ordered pairs in the given relation R. Okay, we assume like that. So where x comma y comma z belongs to integers z. Okay, now we have assumed that order pair x comma y belongs to R. It means x minus y is an integer. Okay, this is a given relation. Similarly, order by y comma z belongs to R. That implies y minus z is also an integer. We assume this is one equation, one statement, and this is another statement. Now let us take this value y minus x minus y plus y minus z, that is equal to x minus z. This means x minus y is an integer, y minus z is also an integer. The sum of these two integers is also an integer. So here x minus z, this x minus z is also an integer. This implies we can write this statement as ordered pair x minus x comma z belongs to R. Okay, my dear children. Therefore, R is a transitive relation. Right. Now, see the next question. Question number 2. Show that the relation R in the set R of real numbers defined as R is equal to set of all ordered pairs A comma B such that A is less than or equal to B square. This is the relation R defined on this set of real numbers. Is neither reflexive nor symmetric nor transitive. We have to show that this relation is neither reflexive nor symmetric nor transitive. Okay, my dear children. Now come to the first relation, that is reflexive. To prove this state reflexive or not, let us consider a real number. 1 by 2 is a real number. We have assumed, we have taken one real number. Now we check. Then 1 by 2 whole square. What is the value of 1 by 2 whole square? 1 by 4. So 1 by 2 is less than or equal to 1 by 2 whole square. In this statement, we are writing these two values, the same number. Instead of writing A and B, we are writing the same values on both sides. So 1 by 2 is less than or equal to 1 by 2 whole square. This implies what you get here, 1 by 2 is less than or equal to 1 by 4. But this statement is false. If we get here a true statement, we can say that that ordered pair belongs to R. But here we are getting a false statement, a wrong statement. This implies that we can say that ordered pair 1 comma 1 by 2 comma 1 by 2 does not belong to R. Therefore, we can say that R is not a reflexive. Understood, my dear children? Right. Now come to the next relation, that is a symmetric relation. Okay. Now let us consider ordered pair 1 comma 4 belongs to R because 1 is less than or equal to 4 square. So this condition is satisfied by these two elements. Therefore, we can say that ordered pair 1 comma 4 belongs to R. But 4 less than or equal to 1 square, if you write in the reverse order, in the place of 1 we are writing 4, in the place of 4 we are writing 1. But this statement is false statement. This implies that we can say that ordered pair 4 comma 1 does not belong to R. Okay, therefore we say that R is not symmetric. Okay, my dear children, right. Now next relation is a transitive relation. Now we assume that two linked ordered pairs, connected ordered pairs like this in the relation R. Let us consider these ordered pairs 3 comma 2 comma 2 comma 1.5 belongs to R because 3 less than or equal to 2 square. What is meant by this one? 3 less than or equal to 4 or not? Okay, we are writing the order P3 comma 2 belongs to R. Similarly, 2 less than or equal to 1.5 whole square. Okay, is it a false statement or true statement? True statement. Therefore, we wrote here order pair 2 comma 1.5 belongs to R. But the new ordered pair, what is the new ordered pair? 3 comma 1.5. By deleting this common element 3 comma 1.5. Okay, 3 less than or equal to 1.5 whole square. If you write the relation between these two elements, whether it is true statement, then we say that that relation is a transitive. Otherwise it is a false statement, then we write it is not a transitive relation. But here we got a false statement. Therefore we can say that ordered pair 3 comma 1.5 does not belong to R. This new ordered pair does not belong to R. Therefore we can say that R is not transitive. Hence finally we conclude that R is neither reflexive, symmetric nor transitive. Understood, my dear children? Right.